So we will be continuing from design of web plate. Earlier we have done the calculation of moment and calculation of shear force. So for the design of web plate without stiffener, if we don't need a web with a stiffen, if we do not want to provide stiffener, okay, then we have to go to this clause and we have to satisfy this equation, okay, where epsilon is this one 250 by fy is equal to, generally it is 1 for fy equal to 250. Then what can be the depth required for the web? The depth will be this one. This is the formula. Okay, we have to keep it 67 in order to get a web without stiffener. Okay, so now mu we have already calculated, and k we have got d by tw. Then fy we know, so the depth is 809 mm, so we provide 900 mm. 809 is the required, so we provide more than that, 900. Then overall thickness of the web, depth we have got 900, so thickness, this is the formula. Okay, so we will get 12.54, so we provide a little more than that. Okay, so we can do it using this also, or using this also. This is coming from here. Okay, either of this we can do. So here we can see that using this condition, that means this one, we get 13.43, and using this condition we get 12.54. So let us take 14, which is satisfying all the condition. So ultimately the web is 900 by 14, 900 depth and 14 is the thickness. Now for flange plate area of the flange is the equal to the moment into the resistance factor into fy into depth of web. Okay, so we get this moment. Now in this problem, this d is actually wrong. It is b for balloon, b for ball. Okay, so now b by tf should be less than equal to 13.6. It is given in table 2, okay, in is 800 2007. Okay, when you go to clause 3.7.2 and 3.7.4, you see a table. Okay, in that table 2, you get this fellow. Okay, for semi compact category, if you want to keep the flange in semi compact category, you have to take b by tf less than equal to 13.6. So we consider it as 13, keeping it in range. Then ultimately b is equal to 13 tf. So area of the flange is equal to width and width into thickness of flange. So width b, already we know it is equal to 13 tf, so 13 tf square, so equal to 11697, which is the area of the flange. So tf we get 29, so that's why here we take 32. That means required is 29.99, so we provide 32. So ultimately flange we provide um, 32 mm thickness, and 13 into 32, which is the width, which is equal to 420 mm thickness. That means 416 we got, but we provide 420. Now we have got the flange, which is 420 by 32, and web we have got 900 by 14. Now we have to check the moment of resistance of the what? We have to check the moment resistance of the flange. So moment, again the formula, this one that you will get in is 800. Okay, so after getting this formula, beta b is equal to what? Zd by zp. Okay, so ultimately we put it here and we get this formula. Now ixx, there is a little bit of confusion here. Okay, ixx will be how much? If I draw it in paint, if I look into this, I this is for 420, this is 32. So if I take the moment of inertia about this. So it will be what? 420 into 32 cubed by 12 plus AR square, isn't it? If I look into this formula, so it will be AR square will be this one. This one is A, which is 420 into 32 into R is this one. This one is how much? This one is 900, isn't it? So this one will become 450. So 450 plus this one is 16. So 450 plus 16 whole square. And there we'll do it from both sides, from this side and from this side. So overall you multiply it by 2. Okay, so that you please check. Okay, then you will get some value here. Okay, and ultimately you section modulus you will get by dividing this ixx with this 482, which is what the depth. Okay, and then ultimately y by 2. Okay, y by 2, this is y by 2, and ultimately you will get zx is equal to 12.96. You will get a little bit different here because this calculation you please check once. Okay, please check once. This one is y by 2. I think there is a mistake here also. Okay, so y by 2, if you consider y by 2 here, you check it please. It should not be 482. Okay, then ultimately after getting this one, you find out the moment, and this is the capacity of moment, and it should be greater than the applied moment. Okay, so now if I do the calculation of this one 482, let me just check once. 482, if this is this is how much? 450 plus 16, isn't it? So this is ultimately 466, isn't it? Plus 16, 482. That means if we calculate it here, 16. Okay, it's fine. This should be 482. Okay, it was just a little bit of confusion. This whole will be 482. Okay, so that is the thing. But you please check this once. Okay, so it should be actually 2 times of 420 into 32 cubed by 12 plus 420 into 32 into 450 plus this one. This is for one side. So there are two sides, isn't it? One is here and another is here. So ultimately it should be multiplied by 2. So let us get back. If we go into the web, we have to check the web for shear. Okay, for shear. So the shear force applied is this one. Then the capacity of shear of the web plate is this formula. Okay, area is web, we know 900 by 14. Okay, this is Fy of the web material 250. So you have to remember this formula, and the capacity that you get should be greater than the applied one. Okay, so it is fine and we don't need any stiffener. And then we have to check for end bearing. End bearing, it is given in the clause 8.7.4 of this of IS 800. Now, bearing, what is this dispersion length? If I try to draw it, if I try to draw it, if if this is the I section along the length, and this is the support, and this is B1, then the dispersion length is B1 plus N1. The load gets dispersed, and N1 is equal to what? It is given here, 2.5 into thickness of flange. So ultimately, this one is the length that I am talking about. So N1 we have got this much, B we have got. So bearing strength required is this one. Remaining values you know already. Okay, so we have seen that the bearing strength is less than the shear force, and we see the bearing at the supports because the shear force is highest at the supports. Okay, so now we got that it is not enough, so we need what? We need stiffeners, or we can say plates. Okay, we need end bearing stiffeners. Now, how do we give the end bearing stiffeners? What is the outstand of the flange? Now let me draw a proper diagram. How much portion is extra here? How much portion is extra? That portion is 420 minus 14 by 2, isn't it? So it is 203. So this you can write 203, 203. Now if I use plates on both sides of the web plate, okay, I'm using plates. So how will it look like? I'm using plates like this, like this. Okay, plates. There will be some thickness of that plate. Okay, we cannot see it here because the image is in 2D. There will be some thickness of the plate. So that thickness is given as how much? 12. And how much we are giving here? 200 length. Okay, now the outstand of the flange, that means how much we can give here should be between 14 of 12 to 20 into 12. This is 168, this is 240. So let us provide 168, okay, into 12. Now what will be the, if we give the this stiffener, what becomes the effective width of the web? Effective width of the web becomes 20 times the thickness of the web. Okay, which becomes 280 mm. So if I try to draw the 3D view, the web is like this, and the plate is going like this. The plate is going in this manner. These are the stiffeners. Now this is becomes 280, 20 times the thickness of the web. So the thickness is 14, and these are how much? These are 168, and this is 12. Now if I have to find out the total area of buckling resistance, it's the total area of the plates plus total area of the web. Okay, 280 by 14. 280 by 14 is this one, and 168 by 12 is this one, both sides. So done. Now IXX, it should be taken like this, along this direction, along this direction. So what is for the stiffeners? It is what? If this is taken along this direction, then this is B, and this is D. D for donkey, B for ball. So for stiffeners we get 12 into total D is this whole 168 plus this one, plus if I consider the web, it becomes B is this one. So it becomes 280 into 14 cubed by 12. So ultimately Ixx we have got, then radius of gyration, then slenderness ratio, then from the slenderness ratio we get the FCD using IS 800. There are various uh, tables given, and from there we have to find FCD using the slenderness ratio that you will know. Then buckling resistance is the FCD into the area. This is area, this is FCD. So we get this buckling resistance, which is greater than the applied force. So it is adequate. Now for the truss girder, this is not complete. This part is just the starting. So I don't know if where the solution is, but the solution is not given properly here. Only the maximum live load till that part only it is given, but other steps are not done. So I think the cross girder part will not be asked maybe in the exam. So this cross girder we have to skip. It is not given. Okay, thank you.